simulated altitude training and hypoxia familiarisation for flight personnel. Here we go. Now, the Earth is a bit shaped like an orange. It's flat on the top and the bottom at the poles, and around the equator you'll notice that the atmosphere, which is this part here, it's called the troposphere, which is the Earth's air, is bigger at the equator than it is up at the poles. So as you go up, you get into the stratosphere, which is beyond the troposphere. You get into space quicker up here at the poles or down here than you do at the equator. Now, as you go up from the Earth's surface, it gets less pressure and cooler and less oxygen. So the temperature keeps falling as you go up, and then if you keep going up, it stops at about this point, and that's called the tropopause, because the temperature stops falling. It falls up to about 35 to 40,000 feet, then it doesn't fall anymore at that point. So I've highlighted the two important things. The rest is just for completeness. You don't need to know this, but I put it in just so you know the layers as you go up from the Earth's surface. Everything happens in the troposphere. Weather happens, water happens, wind and convection happens, and the temperature goes down. In other words, as you go up to 11 miles, 58,000 feet, the temperature drops by nearly 60 degrees C. It gets bloody cold up there. Above 58,000 up to 158,000, which is 30 miles, you've got the stratosphere. So there's some jet stream, that's the very high altitude winds, the ozone layer. The mesosphere is 30 to 55 miles, and then there's another temperature drop there. Goes down to 113, minus 113. Then there's the ionosphere, which is also called the thermosphere. It's 55 to 600 miles. It gets enormously hot, and it climbs from 2 degrees C to 2,600, so it gets incredibly hot. And the significance of this layer lies in that the gases are all ionized, so that if you cook them that much, they all turn into little tiny electrically charged particles. And also radio waves hit this layer and bend. And then the exosphere is true space from 600 to 1,200 miles. It's basically, there's nothing there. It's almost a true vacuum. But all you need to know is that everything happens in the first layer, the troposphere. And the functions of the troposphere are to protect us from radiation, from the UV, to give us protection from the incredible sun's heat, to give us the gases we need to support the life of plants and animals. We need oxygen for animals, and we need CO2, and that's for plants, and water for both. And it also protects us from excessive galactic radiation. The atmosphere doesn't protect us completely, because those cosmic rays go straight through us and the floor, and you know, we don't stop it, but it does reduce it. So that's what the atmosphere is doing. And the troposphere is the efficient zone, and if you split the troposphere up into the bits you can use and the bits you can't use, anybody can walk up a mountain to 10,000 feet, that's not a problem. Once you start going from 10 to 20, you get people with decompression. Well, they get what's called mountain sickness, which is a different problem of not exercising and training enough. They become hypoxic, and they can't really exercise up there, let alone exist up there. And up here at 50,000 feet you need oxygen and all sorts of things to survive. Even in the physiologically deficient zone from 10 to 50,000 feet, you need technical support, supplementary oxygen, pressure breathing, all sorts of things. The physical changes that occur in the air on ascent are you reduce the oxygen, that gives rise to hypoxia. You reduce the pressure, that gives rise to decompression illness and also barotrauma. You can get sinusitis, you can get your eardrums rupturing, you can get problems where trapped gases inside the tissues. And the temperature's reduced, so you get frostbite and cold injury. So if you jump out of an aeroplane at 30,000 feet and you free fall down to 10,000 and then your parachute opens, you might not maintain consciousness during this time. You might become a bit hypoxic. You can oxygen breathe. You can have a little oxygen cylinder on and breathe, so then you are conscious. But you need thermal gear, and you need to be in a wetsuit and all sorts of things. Otherwise you freeze. It's too cold. Now, this is the worst physics because there are 5 gas laws, and they tell us about what sorts of things change in terms of temperature and volume and pressure and movement of gases. At sea level we have a pressure of, in old units, 1 bar. 1 atmosphere is 760 millimetres of mercury, and you're familiar with that because we use that unit for medical, and we also use kilopascals. So 760 millimetres of mercury is an atmosphere, 1 bar is an atmosphere, 101 kilopascals is an atmosphere. Now just this you can remember. As you go up and you get to 18,000 feet, the pressure is half an atmosphere. So it's gone to half. And at 33,000 feet it's gone to a quarter. That's possible to remember. Boyle's law says that if you multiply the pressure and the volume of a gas as you go up, the multiplying factor, the answer you get by multiplying pressure and volume, is always a constant. And balloons at sea level, have you ever seen one of those weather balloons on an airport? They're usually yellow or white, and they're big and floppy, and they just sit on the ground, and they only sort of go up to about this high, and they're just lying there looking a bit like a dead sausage, sort of floppy. And you wonder why they don't fill them more. Boyle's law is the reason they don't fill them more. So you start off down here with a floppy balloon. By the time you let it go, it's got helium in it, so it takes off and heads up. By the time it's at 18,000 feet, you're beginning to use your binoculars to sort of see it, but it's now twice as big as it was on the ground. Because the pressure's half as big, so the volume's twice as big. When it gets to 33,000 feet, the volume's 4 times as big. So this is Boyle's law. And you can imagine if you go up to 8,000 feet in an aeroplane, the volume of the gas inside you expands and you feel uncomfortable because the gas has expanded and the volume's increased. So you don't eat cabbage and beans and all sorts of things before you go up.
Bit of wind happening there.
Yes. Okay. So we can go back one. Dalton's law says that if you've got a mixture of gases and you add up the pressure that each gas makes, the sum of all those partial pressures equals the total pressure. Well, I mean, that's pretty self-evident. If you add up all the parts, you should get the whole. So that's Dalton's law. the sum of the partial pressures equals the total pressure.
Yeah.
Charles' law. The volume at a constant pressure is proportional to the temperature. So if you keep the pressures, you're not going up and down. We're here at sea level.
Constant, yeah.
Constant pressure.
Yeah.
So you've got gas in a bag. If you warm it, it gets bigger, it expands.
Expands, yeah, okay.
Which is not too surprising.
No.
Now the interesting thing is, you can have gas like carbon dioxide in a cylinder under pressure, and if you change the pressure, because it says at a constant pressure, but if you let the pressure off it, then the temperature will go down. So if you have CO2 and you turn the stopcock and the CO2 rushes out,
Yep.
you can catch it in a paper bag
Yeah.
and it turns into CO2 snow, so you can get dry ice
Oh, okay.
from allowing the CO2 to expand.
Okay.
And then the temperature falls.
Okay.
That's
Ah,
Charles's law.
Charles's, okay.
So all these physical laws
Yeah.
explain things
Yes,
that
what
happen.
things happen, yep.
Henry's law, that's pretty good. Henry's law, think of a bottle of champagne. Amount of gas dissolved is proportional to the pressure at a constant temperature. So if you've got a bottle of Coke or a bottle of champagne and it's got a cork or a seal on top, it's under pressure.
Yeah.
If you lift the seal or draw the cork, the pressure's no longer there. The amount that is dissolved is less. So you see bubbles.
So yes, yeah.
And that's decompression sickness. And the final one is the law of gaseous diffusion. The gas moves from an area of high pressure to low pressure, and we'll look at that in a moment. At a constant temperature, the volume is inversely proportional to the pressure. So if you go up, you get a bigger volume of trapped gas in the middle ear and sinuses, the abdominal cavity. It's relevant for people who've got a pneumothorax. In the gut, you get problems. If it's intracranial or intraocular, if you've had a penetrating injury of the eye, you should never take people up to altitude because it can rupture the eye.
Yeah.
The gas expands. It affects equipment performance, endotracheal cuffs and IV fluids and bottles. You need to use PVC bags. No longer do we use bottles anyway. It affects underwater drains and mast suits. Venturi suction is affected and ventilator performance is affected. So Boyle's law affects all of that stuff. It's critical for aeromedical retrieval.
Yes, yeah, I was thinking about this, I have to stay down, I try and keep low.
That's right.
Yeah.
This one is Henry's law. So there you go. Bottle of Coke, bottle of lemonade.
Yep.
The amount of gas dissolved in solution is directly proportional to the pressure of the gas over the solution.
Makes sense,
If you decompress it by taking the lid off, then the liquid becomes fizzy. If you do it to a person, they become fizzy.
yeah.
Okay. The law of partial pressure says that in the atmosphere that we breathe, there's 78% nitrogen, 21% oxygen, and 1% of everything else.
Yeah.
However, when you bring it in through the nose and through the airways down into the lung alveoli, the air sacs, you add temperature, because we can be at the Antarctic and we breathe air in, and by the time it gets inside us it's 37.
Yes,
it's not minus 40.
No, we're good at that.
We air condition the air.
Yeah.
So we add water vapour, we add temperature, and we inject a lot of CO2 in because we're getting rid of CO2 all the time.
Yeah.
So that the partial pressure of CO2 is one of the partial pressures inside the body. The water vapour has a partial pressure which depends on the temperature actually. So at 37 it's always about 47 millimetres of mercury, so it's quite significant. So out of the 760, 47 is water.
Okay.
And it mightn't be out here in the air, it might only be 2 or 3 or 5 or 10.
But what we're breathing out.
Once we breathe it in, it's 47 inside us. And then we breathe it out. So if you breathe it out onto a mirror, the water condenses on the mirror and you get a film of water. That's because there's more water in what you breathe out than there is in the air.
In the air, okay.
Dalton's law says the total pressure is equal to the sum of the partial pressures. That's all right. These are the proportion of atmospheric gas remains constant. So at 18,000 feet, how much pressure have you got? 760 here at sea level.
Okay.
What is it at 18,000
feet?
feet?
You that, didn't you?
Well, just give me a fraction.
Or half.
Okay, it's a half of 760, which is 380.
Yeah. Okay. Yes. Okay.
That's easy.
Yeah.
However, at 18,000 feet, it's still 78% nitrogen.
Okay.
It's still 21% oxygen.
And still one for the others.
The problem is, it's 78% of 380.
Okay.
Not 78% of 760.
Yeah. Okay. Yeah, that makes sense.
And of course, when you add in a certain partial pressure of water vapour and CO2, that takes a fair bit out of the 380. Charles's law says the volume of a gas at constant pressure is directly proportional to its absolute temperature. And the application of that is the falling temperature with altitude. So in other words, the higher you go, the less the pressure, the less the temperature. And a cylinder will cool if you release the gas inside it and take the pressure off it, then the gas that comes out will cool. Fick's law says that the amount of gas moving across the lung tissue sheet or the lung membrane is proportional to the area, the thickness of the membrane, the diffusion constant of the gas, which is its solubility in water and its square root of its molecular weight. So just call it a diffusion constant. And you need to know the area, the thickness and the diffusion constant. And you'll notice that CO2 diffuses a hell of a lot better than oxygen. CO2 needs a very small pressure to drive it. Oxygen needs a very big pressure to drive it across the lung. The area of the lung, by the way, is about the area of a tennis court. So that's Fick's law, and that really affects movement of gases. Fick's law says that the rate of transfer of a gas through a sheet of tissue is proportional to the tissue area, the difference in gas pressure between the two sides, and it's proportional to 1 over the thickness or length of the diffusion path and the diffusion coefficient of the gas. So there you go. The volume flow in litres per minute is equal to the area divided by the thickness times the diffusion coefficient multiplied by the difference in pressure. That's easy. This one is probably the most important thing that happens, and this is oxygen loading at this end and unloading at this end. So we normally have about 100 millimetres of mercury partial pressure in the alveolus. In the air we're breathing now, here at sea level, it's about 160. Can you make a suggestion why it's only 100 in the alveolus and it's 160 out here?
Oh, because we need this air pressure to be stronger than here to make us swap.
No, that's not the reason.
No.
What do we do to the air that's out here?
So
When it starts going in?
Yeah, we humidify it.
Yeah, so you're adding in
moisture.
a partial pressure of water.
Yeah, okay.
And it gets in and
Yeah.
you're adding in CO2.
Yeah.
So you've got two lots of partial pressure.
Okay.
And that tends to displace a lot of the oxygen partial pressure. So instead of 160, it's only down to 100. So that's the normal, fully saturated. At a partial pressure of 100, you're about 100% saturated. 98% or something is your normal oxygen sat.
Yeah.
Now, as you go out in the venous blood, you come out along this line. And when you get down to the tissues out here in the fingernails, you're down at a partial pressure of 40 and the oxygen saturation is about 70. Now there's two tricky things the body does. If you increase the temperature, you move the curve this way.
Okay. Yeah.
If you reduce the pH and make it more acidic,
Yeah.
you move the curve this way.
Okay.
And if you go from arterial blood to venous blood, you find that there's more lactic acid, there's more hydrogen ions, it's more acidic. You've got all these combustion products that are there, so you do reduce the pH, and a working muscle gets hot.
Yep.
So you increase the temperature. So when you get out to the working muscle, you release more oxygen because it goes from up there down to there. You go from 70% saturated down to 50% saturated. And you didn't even have to change the partial pressure. So by this cunning trick of hemoglobin, which releases more oxygen when it gets warmer and when it gets more acidic, the body is able to release more oxygen for the use of the working muscle. So that's a clever trick.
It is, yep.
You come down along that line and then you move down to there.
Okay. Yeah.
Now, what is DPG? Because if you increase DPG, you also release more oxygen. DPG is an enzyme.
Okay.
It's in the red cell. You build more of it if you exercise, if you train.
Okay. So this is this.
So the more you train, the more DPG you have in your red cells. So people who train regularly and exercise aerobically are fitter and they're more able to provide oxygen for their working muscles. The more you train, the better you get at providing the needs of the muscle.
Yep.
So this is the body's own trick, and this one is when you train.
Yeah.
So if you have all of those, you get a lot of extra unloading.
Yeah.
This will just show you a little table. You don't need to remember it, but it just shows you that at 18,000 feet, the barometric pressure is half an atmosphere. Huh? There it is, half.
Okay. Yep. Yeah.
The oxygen partial pressure is no longer 100, it's gone down to 38. That's pretty threatening. You wouldn't like your partial pressure to be 38 because on that previous curve, your oxygen sat at a partial pressure of 38 is only going to be something like 64, about there,
Yeah. Not good.
64, 65, not good. So you're in deep strife when you're down there. 18,000 feet. Venous pressure is a bit less, so you're unloading oxygen as you go from the arterial blood down to the venous blood. You're down to 26. And the differential pressure is not very big. So the P1 minus P2 that moves things across the lung is very low, whereas up here the P1 minus P2 is 60.
So your exchange is 12.
Gas exchange is good at sea level, but it's pretty difficult down there. And the percentage of your saturation is not very big. It's 98 there and it's down to 72 there. We get symptoms when we become hypoxic. We also get signs. What's the difference between symptoms and signs? Signs are objective because they're something you can see and measure. Symptoms are what the person tells you, and they're individual.
Yeah, that's right.
Everybody has different symptoms. So out of this list, you might have a different collection than I would have, and the other thing is, you might have some that aren't even on the list.
Yeah, sure.
So these are symptoms, and an awareness of needing more air, a general feeling of apprehension, feeling of being a bit weak and tired and maybe a little bit nauseated, maybe having a headache, maybe being a bit dizzy or lightheaded, maybe having hot and cold flushes in your face, maybe feeling that you don't care, everything's fine, I'm all right, it's okay, doesn't matter if you're old and grey. You can get a bit stroppy. You can have belligerence, you can have blurry vision, you can have tunnel vision, you can have numbness, tingling, pins and needles, all of those are symptoms. And in the program that you'll see there, we do show symptoms and people have to choose. So while they're fresh in their mind, they've just finished hypoxia and they have to select the symptoms they experienced. And your list will be different, but you'll get it and you'll take it as a printout in your folder. So pilots not only get the little bit of theory, but they also get their own individual symptoms and signs. You can see how much their breathing's increased, you can see from the video that they've become cyanotic, you can see from the errors that they've got that they became confused, you can see that they showed poor judgment, poor incoordination, etc. Okay. Now, is it common that we have hypoxia in pilots? Well, in these 2 years there were more than 100 incidents. And so we can say that the frequency of occurrence is increasing, and as the number of incidents increases, there's an increasing chance of a tragic outcome. Not good. The decompression can either be kaboom, dramatic, explosive. It's pretty obvious. This one was a United B747 leaving Honolulu and heading for Auckland, and the cargo door ripped open and it blew a hole in the fuselage, and 9 people were lost overboard, and the 2 right-hand engines were all smashed by the hydraulic system ripping out. And the aircraft made an emergency descent down to a safe altitude where you don't need oxygen, and they managed to return and land safely back at Honolulu. So that was a pretty skillful, trick. Mostly, it's a much more insidious, unrecognised hypoxia. Decompression you don't know about. There's no guaranteed warning. You do have warning systems, but the same warning system might be available for 2 or 3 different functions, and
Okay.
you don't think you've lost
Might
cabin
be
pressure, you
if
might
you're
think
tired.
it's an electrical fault
Yeah.
or some other problem. So
And in that little bit of time, it might be too
that's
late.
right. Golfer Payne Stewart in Northern Australia, an F-18 got lost. A B-200 King Air went from down there near Karratha all the way up and disappeared off up in the Gulf of Carpentaria. The problem is the effects of hypoxia are pretty subtle and they can come on slowly. And you've only got 3 minutes to really recognise the hypoxia in and get yourself down.
Yeah.
I mean, if you're up at 20 or 30,000 feet, it's not good. You don't have a lot of time. So this is why it's important to have hypoxia familiarisation training. Now, I did tell you about the chambers. This was taken inside the chamber at Point Cook.
A
And
lot of people at once.
oh, there were about 5 or 6 on each side, and one lot takes off their masks and the other lot have their masks on, they're breathing oxygen and they're monitoring the one opposite.
Oh, okay.
So each one is a safety, and there is also a safety person standing there with a mask on.
Yeah.
So the risk of inducing decompression sickness at 25,000 feet is much greater than at lower altitudes, and something like 1 to 2% of the people who go in the chamber end up getting decompression sickness.
Okay.
So chamber training's not very good.
No.
That's why we have that.
Yes.
That's
Stops it.
normobaric. It doesn't change the barometric
No.
pressure.
No.
So it's safe. This costs millions of dollars per year to maintain, and it would cost about 5,000 to 10,000 per person per trip
Okay.
to take them up to 25,000 feet. If you take the cost of maintenance for the year and the number of people you put through, it's an expensive training program. The Air Force says it's good training, but the Air Force has now done a tricky thing, which is to only take them to 10,000,
Okay.
and then they breathe low oxygen mixtures to get them up to 25.
Oh, I see.
So they do a combined
Both, yeah.
altitude decompression and
Reduced oxygen.
normobaric reduced oxygen. This is the sort of cognitive testing for the RAF, but it's not very efficient, it's pretty bad. This is what we used to do at the Monash Medical School and also for the MICA people, which is to have a gas bag with a reduced oxygen, 7 or 8% oxygen, 93% nitrogen, and they'd breathe it, and they'd breathe it in through a one-way mouthpiece, scuba, and then breathe it out to the air. And we'd monitor their oxygen saturation, and the other 4 people would monitor their heart rate and blood pressure, and they do pencil and paper tests all the time to see what their cognitive function was. It was satisfactory, but it's not terribly efficient, and you need all sorts of cylinders and gas mixtures, and it's pretty complicated. This is a better deal. Fully integrated hypoxia education system. What we aim to do with the system that's inside is to educate on the risks of hypoxia. We want to demonstrate how insidious it is, and the only way you can do that is by experiencing it.
Yep.
And if you have the experience, then you know your own individual symptoms, and hopefully you'll be able to recognise it earlier when you see it the next time. So if you have a bit of theory and a bit of practical, you end up, I think, knowing more. We get, by pumping air through the membrane, we get 2 streams, air that's oxygen reduced and air that's oxygen increased. And we have individual stations, and we have a little system that delivers it to the person, And we measure cognitive performance on the touch screen all the time, and we measure the physiological parameters. So it's pretty easy to use the system. The aims are to become educated in the effects and dangers of hypoxia, to demonstrate and measure and record, both in the computer and on hard copy for the pilot to take, their own individual reactions of their heart and their breathing system at the altitude you choose. So you might choose to start them off at 8,000 feet for 2 or 3 minutes and then go up to 25,000 feet and then come down. Oh. The touch screen shows you what to do and how to do it. You're having a theory session to start with, then it tells you finish the theory, you're ready to start the practical, put the oxygen saturation device on your finger. And this was me doing a series of paramedics here before they go in to do the practical training. Now, one of the things that's interesting is that you write with your finger on the screen. Use the edge of your finger on the touch screen, and you can actually write just like that. That was my handwriting, me, in 1964, and this was my handwriting in 2008 when I was hypoxic for 5 minutes, and I don't have the 1964 version, but I can tell you what it was, and it said, "The quick brown fox jumps over the dozy, dozy, dozy," and it sort of went down to the bottom of the page. The reason for choosing this, it's got every letter of the alphabet in it. The quick brown fox jumps over the lazy dog. There isn't an alphabetical letter missing. But the interesting thing is that my time of useful consciousness in 1964 was about 5 minutes and 15 seconds, and here in 2008 it was 5 minutes and 5 seconds. And the visual motor in coordination was just about the same. In other words, my brain had gone into neutral. When you start writing the same word 3 times, dozy, 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 you haven't moved on. Your brain's in a big hole.
It's still on the same word,
The name of that condition is called perseveration. You just stay stuck in the one spot and you can't move. But that's one of the things that you will see. They start hitting the number on the maths and they keep hitting the same one and they don't stop.
It's time to stop then.
Perseveration.
All right. That's very interesting.
And this is oxygen sat, and after these are minutes along here, and this is 100% up there, and this is something lower down here, like 50 down to here. And that's 1, 2, 3 minutes at sort of cabin altitude, and they're able to maintain 95, 96%. And then at this point you start reducing, and they have a reducing oxygen saturation down to something low, and then they maintain that for a little while, and if they've had 5 minutes, that's their time of useful consciousness, then they start breathing air again and up they come back to normal. Notice that their heart rate at about the same time as this starts to go down, heart rate goes up quite a lot, and an increase in heart rate is absolutely universal. Think about it. So, universal. Sometimes people increase their heart rate 40, 50 beats per minute. For me it's much less, it's only about 15 or 20 beats per minute, so I would be on the bottom end of the normal scale. This is breathing, it tends to get more, but it's not as dramatic as heart rate. Heart rate always goes up.
So breathing, that's like respiratory rate, you mean?
Respiratory rate and
good.
depth. Depth.
Depth.
For me, depth goes up and heart rate goes up a little bit. This is me, I think. So heart rate goes up about 15 or 20. Depth doesn't show there, that's rate. Rate doesn't change, but depth increases, and oxygen sat falls off, and then I get back to normal. That's okay. That's maths, that's spatial orientation, that's recognising shapes. The accuracy falls off and the number of errors increases, and the green line is the time it takes you. So to recognise which hand the flag is in takes you longer as you become more hypoxic, and you become more and more and more and more hypoxic, and you get slower and slower and slower and slower. And the same happens here. You still recognise shapes, you don't make any more errors, the error rate's about the same, but you're much slower in processing. And up here you make more errors, your accuracy falls off. And here your accuracy falls off and you're slowing processing. So colour perception, you get much slower at getting the right answer and you make more errors. And this one is memory. I think that one's gone off. So this was the profile. So you get a printout. These are the printouts of what you get. I like to thank the Alfred Hospital Human Research and Ethics Committee, Biomed Tech, which is where we are, Gordon Cable, who's ex-RAF and he's an aerospace medicine consultant in Adelaide, Ian Millar is director of the hyperbaric unit at the Alfred, the air ambulance at Essendon, Monash University, paramedic training and epidemiology, the Royal Flying Doctor Service out at Essendon, the staff at Micah 10 at Moorabbin, who came and helped with all the first 100 subjects, General Flying Services down at Moorabbin, who provided us with 100 subjects, and all the volunteers who underwent the hypoxia training, and ASAM. Oh well, ASAM is the Australasian Society for Aerospace Medicine. So these are some of the incidents from the ATSB database from 1994 to 2004, and there were quite a lot of incidents. That was just put in there for your information, so that if anyone says, oh well, does it happen in the real world, these are Australian ones that happened between 1990 and 2004.